Welcome to another AQA AS Chemistry video. Today I'm going to be doing a video on balancing equations. Alright, let's get straight into it. So, balanced equations. A few key features of balanced equations. They must have an equal number of atoms on either side. You add more atoms by adding reactants or products to either side. Because this has to, remember, you have to obey the laws of conservation of mass. This part here is just talking about, well, these two parts here are just talking about the law of conservation of mass. No atoms can be created or destroyed. So if you add one to one side, it's going to be the same on the other side. I mean, you can have the same number of atoms on one side of the equation than the other side. That's what it's just talking about there. And it's when you're doing this in a calculation, there's no method to do this apart from trial and error. So like this, when you actually do this in exam, you would have known this from GCSE anyway. Your balanced equations, there's no like method to follow through. It's just kind of seeing. There's kind of things you could do to help you out, but it's like not really a method of like working out specifically. It's just like you got kind of seeing how it goes really, but you have to be able to adapt yourself so you can do this quickly. Because you're only going to get 1 mark for balancing the equation. So make sure you don't waste time on that. Why are they useful? So balanced equations can be used to calculate masses or reactants and volumes of gases. And this is you're gonna need to practice to answer these questions, right? So this is what happens in questions. You need to do a lot of practice exam questions or past paper questions to answer these questions, because it's not really like about learning it. It's just about seeing it and doing it. I mean, when you do past paper questions anyway, most of them, if you have a reaction, you need to balance the equation anyway, or at least check that it's balanced equation. So one of the things is titration, right? And if you did triple science, you would know more about titrations. But if this is the first time, then titrations are an experimental technique for finding the concentration of solutions. Titrations use balanced equations to calculate the concentration of an unknown solution from a volume of a known solution. The experimental technique involves the use of a burette and often an indicator. A small volume of solution is dropped from the burette into the reaction flask, and this is repeated until the indicator shows no further reaction happening. So this is how titration actually works. It looks really complicated and everything like that, but what you need to understand is that you're just trying to use this to work out the concentration. If you don't know the concentration, remember what you need to work out the concentration. You need the concentration. Any space to write? Go right here. Moles over volume. Now, if we have the moles of compound, if we do a if we have the concentration of one compound, when we balance equations, as I'll show you an example later on, but if we balance the equation and we work out, and we know the concentration and the volume of another compound, because you first of all you need to write a balanced equation of reaction, and then you'd write. First of all, actually, you know what? I'm making this more complicated than it really is. First, we need to actually understand what's going on. First of all, right? I'm gonna explain what's going on. All you have is that in this conical flask, right? You pipette an acid, for example, and you have a known compound here. You know what the compound is, but you don't know its concentration. You know its volume though. You have a fixed volume in your pipette, right? And then you'd add an indicator. That's just to tell you when the reaction is going to stop, right? And all you're doing is that you're mixing in another compound with a known concentration and volume. For example, you can use a base, right? In this case, a base. This is a neutralization reaction, so it should have. I can clearly see the use phenolphthalein. I think they use phenolphthalein because it's got pink here. And it's becoming more basic actually, but the point of this is that if you know the concentration of this, and you know the volume that you have, right? And the volume of your amount you use is the amount that's been used in the reaction. The volume is the amount that you've been used in your reaction. So you're just trying to find out what the moles are, and once you've worked out the moles, and you know the mole ratio from balancing your equation, you can then work out the moles of your compound in your conical flask. If you have that and you have the volume, then you can work out the concentration of the compound in the conical flask. This isn't the best way for me to explain it. I'll do a question it's a much better way of explaining it. But I'll probably do another video just on titrations. But the idea is you have a known volume of an unknown a known volume of a compound, but you don't know its concentration or its moles, and you're using the concentration of another compound. Once you balance out the equation, you'd use the concentration of another compound, and you'd find out how much of that volume it would take to actually cause until the reaction is gone to completion. The way you find out your reaction goes to completion is you use this indicator here. Once it changes color, you'd know the reaction is gone to completion. But if you know it, say 30 centimeters cubed of a compound was used, you know that's the volume. That's what we call that the titer volume, right? And that's the titer volume is the volume that you'd have for your reaction, for that it's the volume that you'd use for that compound in that reaction. So then you have the concentration, you have the volume, you can work out the moles. You use the mole ratio to determine the moles in your conical flask. Concentration, you use the moles of the volume. You already have the volume, work out the concentration. And that's what it generally is. This isn't the best way of me explaining it. I'm trying to broadly explain it, but I'll probably make another video to try and properly explain it. But that's why it's important to understand balancing equations, because once you balance your equations, you can work out these things. So I'm gonna go through one question here. So what's the mass? Answer this question here. What's the mass of water? So what mass of water will react to 15.98 grams of bromine? 3-mark question. Pause the video now and try and answer it. Alright. I assume you've paused the video now and you try to answer it. If you just want the answer to it, just skip to when I finish the question, but I'm just going to go for it. So, what mass of water will react to 15.98 grams of bromine? First of all, the first thing I'll do is write out the equation, right? So, bromine it'll probably be in a solution form, to be honest, but bromine plus water. This is actually a disproportionation reaction. It happens with halide ions when they're reactive. So halogens, sorry, not ions. When halogens react with water, they actually go on something called a disproportionation reaction. A disproportionation reaction, I don't think you need to know it just yet, but you need to know it in your exam. But what disproportionation reaction is when it's when your reactants are when your reactant is both oxidized and reduced at the same time. I believe this is a disproportionation reaction. So this is just 0, right? X minus 2 plus 1, x minus 1, 0, x equal to plus 1, x plus 1 equals 0, and that's x equal to minus 1. Yeah, so this is a disproportionation reaction, because if you look at the oxidation states of bromine, it's plus 1 and it's also minus 1 in both sides. So it's being both oxidized and reduced at the same time. And that's what it's. But anyway, that's not really related to the question. I just, I just saw this here and I thought it'd be, kind of interesting there. But I'll just go on to what the actual answer is. So I kind of went off topic there. But anyway, so when I'm answering this question, I would write out the equation, make sure it's balanced, right? BR2, this how I actually balance my equation. I do like this. I can sometimes just look at it, but if there's too many things that's going on, I just write out what I have. So I have there's Br, H, and O. There's 2 bromines. This is something that you should know from GCSE, but in case some people just didn't know it this way, you can write this way. This is how I learned it from my teacher, Miss Coilas, a really long time ago. There's 2 bromines here. Hydrogen is 1, oxygen is 1. It's balanced on both sides, so that's not going to be a problem. what's the mass of water? What mass of water will react to 15.98 grams of bromine? First of all we need to work out the moles. We have the the we have the mass. We can work out the MR of bromine because we have the periodic table. Then so moles is equal to the mass over the MR. So moles of bromine, Br2, is equal to the mass, which is 15.98, over 2 by the MR of bromine, of one single bromide atom, 79.9. But since you have two of them, it's 2 times by 79.9 because it's Br2. And that's the same as 15.98 over 80 times by 2, 160, minus the 2, 159.8. And that's, oh, this is actually just 0.1. Yeah, 0.1. Well, they probably made it in that way anyway, so that's 0.1 moles of Br2. It's a 1-to-1 molar ratio. You have to see that it's a 1-to-1 molar ratio here, right? For every 1 mole of Br2, there's 1 mole of H2O. So we can just write 1-to-1 molar ratio. You should spend 3 minutes on this question, but I'm just trying to explain to you, break it down for you. So I'm spending a bit more than 3 minutes. I'll probably do the next one in less than that, but we'll see. We'll see. Moles is equal to, they said what's the mass of water, mass of water, right? So we have the moles, we have the MR also. If moles is equal to the mass of the MR, the mass would just be mass of water is equal to moles times by the MR. So that's 0.1 multiplied by 18. If you didn't know, 16 plus 2, or 1 plus 1, that's just 18, right? 1.8 grams. So the answer is 1.8 grams. Ideally, in the real exam, you should spend at least you can do this in probably less than 2 minutes, like 1.5 minutes, really. That's how much time you should spend doing these questions. Once you do enough of them, you can do them really easily. As I said before, I'm just trying to break everything down for you as simple as possible. I know it might be jarring to listen to me speaking like this, but just, if you want to just skip to the next part of the video, you can just do that. But just trying to explain, right? Ionic equations. So ionic equations are used to describe the reactions in solutions. You have ionic solids. So ionic solids will dissolve in solution and will split into their constituent ions. This is very important because this was something that's very important for year 2 chemistry. Just understanding this briefly, all the chemistry in general, but especially when you're doing ionic equations, you need to understand that when you're talking about an aqueous compound, right, it just means that it can be dissolved in water. And when you dissolve something, you're breaking it down. You'll learn about the enthalpy of solution, enthalpy of hydration in year 2, but just understanding ionic solids and how they're broken down, and ionic equations, especially ionic equations in year 2. You need to be able to understand this, right? So NaCl can be broken down into Na plus, which is aqueous, and Cl minus aqueous. It's meant to be Na plus and Cl minus. They're still aqueous because they're still dissolved in a solution of water, but they are broken up into their individual ions, right? And the charges always cancel out. Reacting in solutions. So some of the ions dissolved in solution will react, but some of the ions dissolved will not be involved in any reaction. These ions are called spectator ions. So, if I had Na2SO4, right, and I dissolved that, the spectator ions would be the Na plus ions, really. Unless they specifically talk about they want the Na2, talking about Na2 plus ions, but generally, when we're talking about spectator ions, the ions that just don't get involved in the reaction, they kind of left out. You'll see them, actually, you can see them mostly in if you go to organic chemistry and you go to some of these substitution reactions or these elimination reactions, where they'll have certain parts just are spectators and they don't get really involved in reaction. Those H pluses or those Na plus, or like for example, in a nucleophilic substitution reactions that you involve hydroxide ion, they use NaOH, right? And the only part we actually care about when we're doing nucleophilic substitution reactions is the OH, because that's the actual nucleophile. The Na plus, that's a spectator ion, doesn't get involved in the reaction, and that's what it is. Just ions that just don't really get involved in the reaction. We don't really care about them really. All right, ionic equations. So ionic equations are equations that have excludes all the non-reacting spectator ions. So when we write our ionic equation, we don't include the spectator ions, which we don't regard them. The charge on either side of the ionic equation should always be equal. State symbols, and I know you guys know what state symbols are, but I'm just gonna quickly brush through them. There's a little part at the end that I just wanna talk about. Please just make sure that you should just get this right. So state symbols are letters that tell us what state of matter a substance is. There are 4 different state symbols, obviously: solids, magnesium, and sodium, both solids. Liquid is pure solids, so water and mercury at room temperature is liquid. Aqueous is used for aqueous solutions, substances that have been dissolved in water. So if it's not a pure solid or something's been dissolved in a compound in a solvent, that is an aqueous solution, and therefore it's used more often than liquid. You never really get much in chemistry. You're more likely to get the aqueous compounds, right? So sodium hydroxide, that's, to get this kind of compound, you're never going to get sodium hydroxide. Can you get sodium hydroxide by itself? Would you? No, I feel like that would just be the ions. It would just be that. No, you'd have it as an aqueous solution. H2SO4, that's going to be an aqueous solution. Gases, everyone knows gases. They're used as the little g represents gases, state symbols. H2 and CO2, you already know what they are. But why they're useful is because state symbols are useful to chemists, because the state a reactant is produced in can affect the experimental technique. For example, you don't want to carry out a reaction that generates 30 moles of CO2 gas in a 10 centimeter cubed vessel, because it would explode, right? It's important if you do these reactions and you know what the product is, and you know you're gonna get something that's like, for example, a gas, and you know that gas, if you're producing 30 moles of gas in a 10 centimeter cubed vessel, that's too much pressure. If you're producing, this would never happen, but if you were producing the 30 moles of CO2 solid or liquid, that wouldn't be a problem, because you know that that solid or liquid wouldn't be it wouldn't be high pressure, right? The gases move around more freely. You already know what states matter, but you know gases move around more freely, and it would put more pressure, and they collide against the walls of the container much more, and that would cause that massive pressure, and in this case it would cause too much pressure that it would explode, right? So understanding state symbols is just important to understand for experimental reasons. I say these things, I know they don't sound like they're relevant to your exam or anything like that. I say this because you might get a question that might just ask, why is it important that you know the products of this reaction? And even when in year 2, when you're talking about entropy, gases, you're understanding gases, solids, and liquids, and how they would affect the entropy. You learn more about entropy. I'm going to make a video about entropy later on, but knowing that state symbols would affect entropy much more dramatically, because they increase disorder more because they move around more. That's why I say these things. But yeah, that's what you need to tell for that. All right, I'm going to stop talking now. This is going to be the last question, and I promise I'm not going to be talking too much more. But yeah, so 20 centimeters cubed of H2SO4 of unknown concentration is titrated with 0.1 moles per dm cubed NaOH aqueous. The titer measured is 15 centimeters cubed. What is the concentration of H2SO4? 5-mark question. Pause the video now. Try and do this in 5 minutes. All right. I made the assumption that you've spent 5 minutes to try and answer this question now. Right. So what I was talking about with this question, right, is what this question is: if this 20 centimeters of H2SO4 concentration is saturated with Yep, so imagine this H2SO4, this acid, right? It's the same thing as actually the one before in it already. Imagine you have 20 centimeters cubed here in this. You've pipetted 20 centimeters cubed into a conical flask, right? You don't know its concentration, as I said before. You don't know its concentration, and it's titrated. When you're titrating it, you're putting it in this burette, you're reacting it with, you're putting it into a titration vessels, into a titration vessel, which is the burette, right? You put 10 centimeters, how many you put in there? It's going to be a large one. It doesn't matter. You don't need to know that. It's going to be, it's usually 250 centimeters cubed. That's how long the burette is. Yeah, but that's not relevant to that. You have, but you know the concentration of that is 0.1 moles per dm cubed, right? Of sodium hydroxide, right? And they put the indicator in here, and in order for the full reaction to occur, it said 15 centimeters cubed of it was the titer. So if you release 15 centimeters cubed of this NaOH into this side here, 15 centimeters cubed of this NaOH into the conical flask, the color change will happen. When you're doing a titration reaction, your teacher will go into more detail about how the titration reaction actually happens. You actually unload little bits of it. You open and close the tap every 2 increments until you get to the last one, which will be every half increment. And you keep swirling your titration, your conical flask, to actually, because you need to actually stir your, or I guess swirl your conical flask in order for actual color change to occur. Right? But if you know roughly that, in this case, they already told you it, but they've told you at 15 centimeters cubed, once you've used 15 centimeters cubed of your titer volume of sodium hydroxide, there's a color change to reaction. So you know 15 centimeters cubed is enough for the full reaction to happen, right? It means that your H2SO4 is the limiting reactant or limiting factor, because this is the one that's getting used up. This is your limiting factor is your H2SO4. That's the word I was looking for. Right. I'm actually gonna start answering the question now, but I just wanted you to understand what's going on before I actually answered the question. Alright, so this is what's going on. And in reality, when you're actually calculating these questions, this is what you do. If you did the experiment, this is why you do, and you do even in your actual experiment, you're required to actually know your titer, to calculate all these things out on what, and there's calculations you do before your experiment and calculations you do after your experiment, and these are the things that you'd carry out, right? Okay. If you just want the answer to this question, you've already answered it, feel free just to go to the end where I've actually fully answered it. But am I going to do this in 5 minutes? No, I'm going to try and explain to you what I'm doing as I'm doing it. But yeah, if you want to go straight to the answer, go straight to the answer. But I'm going to try and break it down for you, right? If you needed help here. Right, so when I look at this question, I would write down the equation for this question. So it's H2SO4. This is a neutralization reaction, right? So it's going to be, you're going to form salt and water. So H2SO4 aqueous plus sodium hydroxide. Need a bit more space. If I'm balancing equation, I need to leave a bit of space in case I have another number that I want to put there. Aqueous goes to form, it's actually it's Na2SO4. It'll be Na2SO4 because it's one, yeah, Na2SO4 aqueous, yes, that's a salt, plus H2O, salt and water, your salt and your water, right? If this was a an ionic equation, it would just be SO4 plus an OH minus goes to form an SO4 2 minus ion. The Na2 here, Na, and that's just the those spectator ions. I could write an ionic equation, but we're not looking for that right now. I'm going to try and explain to you. I mean, would it provide you the same result? I'll do that later. I'll do that at the end of it, but first of all, we need to balance this out, right? How I balance it out? HSONA. HSONA. We've got 3 hydrogen atoms. If you count them up, it's 3 hydrogen atoms. 1, 2, and 3. S1, O is 5, and then sodium is 1. Hydrogen is 2 here. S is equal to 1. Oxygen is equal to 5. Na is equal to 2. So I can clearly see here there's 1 more hydrogen on this side and 1 less sodium on the, so 1 more hydrogen on the reactant side and 1 less sodium on the reactant side. But the sulfur and the oxygen are the same. So I'll try and increase this by 1. So 2. That means I have 6 now oxygen atoms, and yes, 4 hydrogen. So I want to increase this by 2. So that's 4. That's balanced. 4 is the same number of atoms on either side now. 4, 1, 6, 2. That's a terrible one. Four, 1, 6, 2. 4, 1, 6, 2. Right. I know I'm going really slow, but I'm trying to explain to you guys. If you want to just skip to the end, go to the end. Alright, what I'd write down now is or the concentration, the moles, and the volume. Concentration, moles, volume. Concentrations is, they haven't given you the concentration. No, that's what we're trying to find out. Moles we don't know, but we do know the volume. We do know the volume is 0.02 decimeters cubed, or 20 centimeters cubed. But you know you're going to use decimeters cubed, so divide that by 1,000 to get 0.02 decimeters cubed. For our sodium hydroxide, we do know its concentration. We know it's 0.1 moles per dm cubed. If you're just doing this as a reaction, you don't have to write down the units. But we don't know the moles. We do know the volume, which is 0.015 decimeters cubed, right? What we're trying to find out is we need to get to here. We're trying to get to here. How can we get to here? We can work out the moles. We know we already written out the equation. So let's just do that now. If we can find out the moles of this, we know that we can use the mole ratio to find out the moles of this, and then we can use, once you have the moles and the volume, you can work out the concentration. So moles of sodium hydroxide. So moles of sodium hydroxide. First of all, actually, let me just do moles is equal to the concentration is equal to moles over volume. Therefore, moles of sodium hydroxide are equal to the CV, or concentration times by the volume, and that is just going to be the same as (0.1) multiplied by 0.015. That's equal to 1.5 times 10 to the power of minus 3. Minus 3 moles. Right, we know that. So we know this is 1.5 times 10 to the power of minus 3. But it's a 2-to-1 mole ratio, or 1-to-2 mole ratio. 1-to-2 mole ratio. So if we want to go get the moles of H2SO4, we have to divide this moles of sodium hydroxide by 2. So moles of H2SO4 equals 1.5 times 10 to the power of minus 3 over 2. And that would be equal to 7.5 times 10 to the power of minus 4. Yes, it should be minus 4. Should I turn on? Let me just double check my calculator to see what I have. That should be right. That should be right. Before I make a dumb mistake. Good, I'm not done. Right. Allegedly. Right. Where was gonna go from here? Right, actually, no, we have it. We already have this now. So we have 7.5 times 10 to the power minus 4. We can now work out the concentration. Concentration of, well, concentration, that's a terrible conc of H2SO4 is just equal to 7.5 times 10 to the power of minus 4 over the volume, which is 0.02. Therefore, our concentration of H2SO4 is equal to 0.0375. 0.0375 moles per dm cubed, or how I would usually write them. Actually, it's not roughly, it's the same thing. 3.75. Actually, how much are they giving you in the question? Sorry, the place I copied it from was actually 0.1. There's not. 3.75 times 10 to the power of minus 2. Yes. Moles per dm cubed. I was just thinking because the place I copied it from, because I have copied this, they use three significant figures. I just didn't copy it down, and that's my bad again. This should be, but imagine this is three significant figures, right? So 0.100, 15.0, 20.0, and that would be, this is my bad. I should have done this video much better, but that's how they use the least number of significant figures in the question. But you know what? I'm gonna use what I have here, right? And they've said 20 centimeters cubed, 15 centimeters cubed, two significant figures, right? Or I'm not gonna go down to 0.10, right? Let's just use what they have here, and it'll be 0.38. Or 3.8 times 10 to the power of minus 2 moles per dm cubed. In chemistry or in other sciences, you don't actually have to write three significant figures anymore in brackets. You can just leave it at that. Alright, I know this is a bit of a long-winded video, but hopefully this video was helpful. I'm trying. Allow me.